Okay, we have unit 4, lesson 3, quantum theory and the atom. We're beginning with the atomic emission spectra. And I hope this is not going to be a totally foreign concept because I kind of taught it earlier today. Every element that we know of gives off a certain frequency of light. Everything. That's how we can tell what one element is versus another because of the light that it gives off. Here's a few things we've already known. Electrons orbit the nucleus of an atom. No surprise there. See if you guys can fill in the blank. When electrons gain energy, they become blank. What was the word? Excited. Good. They get energized. We don't say energized, we say excited. Now, let's make something clear. When you have an electron on the ground state and it's going from ground state to excited state, is it bringing in energy or is it releasing energy when it's going from ground to excited? It's gaining. So this is where I think if you just use your brain power, this will make sense because chem can be hard, right, Jad? If you're gaining energy, yes or no, are you giving off light if energy is coming into you? What about when you're losing energy? Are you giving off light? That's when you're doing it. So think of a firework. You've all seen them. When you see those fireworks blow up in the sky, are those fireworks absorbing energy to become excited? Or are they releasing energy to go back to the ground state? Exactly. All those different colors you see is energy release. When you see a bomb go off, come on, is energy being released by the bomb or absorbed by the bomb? It's being released, and you see it. That's why I want you to understand, is when you see light, energy being released. If I don't want you to do this, but if you look at the sun, don't stare at the sun. Is the sun releasing energy or is it absorbing energy? It's releasing it, and we see that. That's why I need you to get it. If you get that, you'll understand this. When electrons release energy that they gained, they emit light. And that is super important. Every element emits a unique frequency of light. Halen is a unique human being. There's more than 8 billion humans on Earth. There is not a single one that is like her, looks like her, acts like her, is her. She has unique DNA, very unique, one of a kind. Every element on this periodic table has a one-of-a-kind light it gives off. And I want to remind you again, this is how we can look out in space and know what stars are made out of, know what planets are made out of based on the light that they give off. This is the atomic emission spectrum. Why is it important? Why am I teaching this? The reason why is because it's used to identify elements. So I want to give you a scenario here, okay? I'm just making stuff up, but the logic is the same, okay? You ready? Watch this. Let's say that iron gave off a frequency of 2, you don't need to write this, of 2.3 times 10 to the 20th hertz. Let's just pretend, okay? Totally pretend. Uranium gives off 9.7 times 10 to the 50th hertz. And then thorium gives off 8.8 times 10 to the 50th. There's an asteroid that hits Earth. Boom! Right in your backyard. It's about the size of a chihuahua's head. Not a big deal. We have no idea what elements this is made of. So what we do is we shine light on it so that it will release light. Or maybe we energize it, we excite the electrons so light is given off. So we do what we need to do to make this little meteorite emit light. And when it emits light, we use a device called a spectrophotometer. It is a device that measures wavelength and frequency of light. And after all of our tests, we realized that the light given off by this mystery rock from space has a frequency of 2.3 times 10 to the 20th hertz. So scientists get out their little catalogs of every element, and they find out, okay, what element gives off 2.3 times 10 to the 20th hertz? What element would it be? Iron. Then we now know, oh, this thing is made of iron. It came from space and it has iron in it. That's how we learn this stuff. Everything gives off its own unique light. It could have been uranium, it could have been thorium, it could have been something that I didn't label up here. Zinc, phosphorus, who knows? But everything gives off its own light. We use this to identify elements. All right. I'm going to start to wrap things up. Let's introduce you to another very important guy, the Bohr's model of the atom. Did anybody see the movie over the summer called Oppenheimer? You saw it? Niels Bohr was in the movie. He kind of consulted Oppenheimer on the bomb. He's a Danish physicist. So that's from Denmark. He determined electrons have a ground state and an excited state. You've already been taught this. The ground state is the lowest allowable energy state. Excited is when it has actually gained energy. But ground is as low as you can go. It's like your base form. Bohr also determined that electrons orbit the nucleus in designated energy levels. So you guys have different electrons at different energies. He determined that electrons orbit the nucleus in designated energy levels. So I'm going to draw this for you, but here's the problem, and this is where I'm going to start to wrap things up for today. He only concluded this with hydrogen. Here's the problem with hydrogen, everybody. There's more than 118 elements today on the periodic table. He figured this out with the smallest atom in the universe. What about the more complex ones? We'll have to deal with that tomorrow. But here's how this looks. Here's the nucleus. Here's an electron. But compare it to this. Here's the nucleus. Here's an electron. Which nucleus is further, or which electron is further away from the nucleus? The second one or the first one? Now, what is the charge? Do you remember what the charge is of the nucleus of an atom? It's positive. What is the charge of an electron? Negative. And I said yesterday, what keeps electrons from going towards the nucleus? Opposites attract. Well, it depends on how excited the electrons are. And this, again, if you can pay attention for about 1 more minute, and hopefully you'll get this. This electron is weak. It is really close to the nucleus. It can't resist that attraction. This electron is strong, and it can resist that attraction. That's an excited electron. This is not. The problem with this model from Bohr is that he only figured it out for hydrogen. It really does not apply to any other element. And so we will have to get into that tomorrow. We'll pick up where we left off with this. I'll rehash this material and we'll continue because I really want to get you guys in a good place set up for Monday.